Hi everyone! Today we will be talking about free falling objects. Imagine you're inside the room talking to somebody with your cell phone and then suddenly your phone slips from your hand and falls to the ground. How about when you're in your office and then you accidentally hit your pen, causing it to fall to the ground? Does it not make you wonder how long it took for the object to reach the ground, how fast the object was moving, and the displacement of the object? These are some situations where free-falling objects are present. How about we discuss what free-falling objects are? A free-falling object is any object moving freely under the influence of gravity alone. Any free-falling object experiences an acceleration whose magnitude is g is equal to 9.8 meters per second squared and is directed downward. Acceleration due to gravity is equal to negative g, which is equal to negative 9.8 meters per second squared. This is the same for all free-falling objects. Kinematic equations may be used to solve any problem involving a particle under constant acceleration in one dimension. Therefore, free-falling objects are under the uniformly accelerated motions, and we can use kinematic equations. How about we let our friends Pat, Ray, and Arvin take over and explain to us how the kinematic equations were derived and show a few examples about free-falling objects.
So today we will be discussing the kinematic equations and how they were derived. The first equation is the average of the velocities. The average of velocities will be equal
to the initial velocity plus the final velocity divided by 2.
These are all vector quantities. This will be equal to delta x over delta t. We will equate these two equations and we will get the second equation, which is xf is equal to
xi multiplied by this equation, which is plus 1/2 vi plus vf. Since this will is this and there is delta t here, delta t will be multiplied here times delta t.
This is our second equation. The acceleration is equal to
the final velocity minus the initial velocity over delta t.
Delta t is equal to
Final velocity minus initial velocity over acceleration,
which came from here. Our third equation is the final velocity, which will be equal to
the initial velocity plus we cross multiply this and then we will transpose this initial velocity to the other side, making a positive initial velocity plus the acceleration times delta t.
From our third equation, we can get our fourth equation. We can get the fourth equation by substituting this final velocity to this equation because there is a final velocity here, making xf is equal
To
to
xi plus 1/2 vi plus a or acceleration times delta t multiplied by another delta t.
We will simplify this equation by xf is equal
To
to
xi plus 1/2 2vi plus acceleration times delta t. Times delta t.
We can apply the distributive property of multiplication into this equation, which will cancel the 2vi, and then we will get this equation. We're almost done. We will just finalize this equation by multiplying these two delta t's. We will again use the distributive property of multiplication here in this equation by distributing the delta t. So our final fourth equation will become
xf is equal to xi plus initial velocity times delta t plus 1/2 acceleration times delta t squared.
So for our last equation, equation 5, we will derive this equation from equation 2. So our equation 2, we will start with equation 2, which is
xf is equal to xi plus 1/2 initial velocity plus final velocity times delta t.
we derive the equation for delta t, where delta t will be equal to.
Final velocity minus initial velocity over acceleration.
So we will substitute this delta t with this equation, making our equation to this xf or our final position is equal
The
to
initial position plus 1/2 of this, we will substitute it here, making 1/2 df minus di plus times df minus di over acceleration.
We can simplify this by multiplying these two, and we will get xf is equal to
xi plus 1/2 times 1/2 times acceleration times df squared minus di squared.
To make this equation favorable for the final velocity, we can cross-multiply it here by transposing the initial velocity here, the initial position here, making
xf minus xi cross multiplied by 2a will be equal to the final velocity squared minus initial velocity squared.
we will also transpose this initial velocity to the other side, and our final fifth equation will become vf squared is equal to
di squared plus 2a times xf minus xi.
So in this example, we set a reference point at the top of the building. So YF is equal to H, which is the height of the building. So to compute for the height of the building, we use the kinematic equation. So YF with respect to Y is equal to
The initial position plus the velocity initial plus 1/2 acceleration with respect to y and the delta t.
So YF is equal to YI plus velocity initial plus 1/2 acceleration with respect to Y EF minus TI, or the final time and the initial time. Since the stone is dropped from the top of the building, the initial position is equal to 0, the initial time is equal to 0, as well as the velocity initial is equal to 0. So yi is equal to 0 plus velocity initial is equal to 0 plus 1/2. Since this is a free fall example, negative 9.8 meters per second squared. And the initial time is equal to 0, so the remaining will be the TF, or the final time, which is equal to 4.5 seconds squared. Should be squared. So we compute for the YF. YF is equal to
1/2 negative 9.8 meters per second squared acceleration due to gravity times the final time, which is 4.5 seconds squared.
So YF is now equal to negative 99.225 meters. So basically, there's no negative values when we are talking to the height of the tower or the building. So the answer is 99.2 meters. So the height of the tower is equal to 99.2 meters.
In this problem, we are given a stone at rest at the top of the building, which is dropped from a height of 30 meters. We are asked to find the time it takes for the stone to reach the ground and the speed of the stone at impact. First, we'll be finding the time it takes for the stone to reach the ground. So we'll be using this kinematic equation. We'll be using this equation. We'll be using the top of the building as our reference point, which makes our initial height to be 0 and our final height would be 30 meters. Our initial velocity would be 0, will also be 0, plus 1/2 acceleration, which is constant, negative 9.8 meters per second, also multiplied to final time minus initial time squared. Our initial time would be 0, and also here we can derive this equation to get the final time. Square root of 2 multiplied by our final height, or the height of the building, which is 30 meters, And it would be negative because our initial height is at the top of from the top of the building, which makes the final height, which is at the bottom of the building, be negative over acceleration, which is negative 9.8 meters per second squared, which makes our final time to be 2.47 seconds. That's the time it takes for the stone to reach the ground. Next, we'll be finding the speed of the stone at impact, which is VYF. And with this unknown, we'll be using this formula, kinematic equation. Since our initial speed is 0 because the stone is at rest initially, and our initial time would also be 0. With this equation, we can derive and find the final velocity, which is not constant. And we can substitute the values here in our equation, our final derived equation, which is square root of 2 divided by 9.8 meters per second negative. And our final time, which is this one, what we got earlier, 2.47 seconds. And from this final derived equation that we have, we can substitute the values and get final velocity would be equal to
Negative square root of 2 multiplied by negative 9.8 meters per second squared, multiplied by 2.47 seconds.
which is our final time. And with this, we can get our answer, which is 24.2 meters per second. That's the speed. That's the speed of the stone at impact on the ground.